Welcome, everybody. And I want to first start off by thanking Meta and Luca for inviting me to spend some time talking to you about the future with QUIC. My name is Jana Iyengar. I work at Fastly. And today I'm going to be talking about three things. What is QUIC? What is QUIC's immediate value proposition? And what does QUIC enable for the future? You might think of this also as a short primer on QUIC. It's going to be pretty short. But how did we get the world interested in QUIC? That's an important piece that I want to spend some time on. And I want to talk about what is the real goal, or what was our real goal in getting QUIC deployed after that. Before getting into the weeds here, let me just start by sharing with you who I am. My name is Jana Iyengar. As I said, I'm the product lead for infrastructure services at Fastly. I'm an editor of the IETF QUIC specifications. I am the chair of the IRTF's congestion control research group, and I have been working on transport for over 2 decades now. And I've been working on QUIC for almost 1 decade. So let's start with what is QUIC. You might have seen this picture before, but I'll walk through it quickly. You see on the picture, the left side of the picture shows you a typical HTTPS stack with HTTP 1 or 2 sitting on top of TLS, sitting on top of TCP. On the right side, you see an HTTP 3 stack that sits on top of HTTP 3 sitting on top of QUIC, which has TLS 1.3 sort of in it, but that sits on top of UDP. And then the piece that I just said about TLS 1.3 sitting in QUIC is kind of important. QUIC and TLS 1.3 are tightly wound together, and HTTP 3 is simply HTTP that runs on top of QUIC. So this is what you might have heard for the past few years if you've been paying attention to QUIC. And there are many talks that I and others have done about the performance benefits of QUIC and HTTP 3 for the web and for video. Do a quick search on YouTube and you'll find these. My talk today is not about these benefits. Today, I will dig into the design, our real rationale, and the somewhat intended consequences of our design that you're seeing play out. First, what are the features of QUIC? I'm not going to go into all the features, of course, but the big one is multi-streaming, or multiple independent ordered byte streams. This is a super useful abstraction for HTTP, but it's also a super useful general abstraction. QUIC streams are lightweight. Each stream can be created and destroyed easily. You can effectively treat a stream as a message abstraction if you want. So while we never really advertise this, QUIC can simply reliably carry messages, where messages are streams. Though admittedly, you might need to optimize your stack to do this efficiently. The early napkin designs of HTTP3, in fact, used streams in quite different ways to enforce message boundaries as well. And some video streaming designs use using QUIC talk about using streams as the abstraction that maps to frame boundaries. So streams is a powerful abstraction if you implement it right. And you want to implement it as lightweight, truly elastic in size, and optimized for both message and stream-like users. Also, for the transport nerds in the room, you can build partial ordering on top of this. QUIC is UDP based because QUIC gets through most networks. Now, again, we've said this for a long time, but why did we build it over UDP? Was this a short-term thing? Did we foresee like wanting to move it over IP? Not really. This was a recognition that this is the internet that we will have for the foreseeable future. Importantly, this would give us the agility and the ability to rapidly innovate. Now, this is really important. Being on top of UDP does not necessarily mean that you're in user space. However, being on top of IP almost certainly means that you are in the kernel. And that hampers and hinders agility and the ability to deploy things rapidly quite a bit. So we built it on top of UDP primarily because we wanted it to be easy to be built in user space and for us to be able to rapidly iterate on the protocol and deploy it quickly as well. Third, and perhaps most importantly, we baked encryption in. And we clearly always said that this was to protect all the application data and the transport metadata, which is true. But the other important reason was to prevent the protocol from becoming ossified. TCP is ossified. You cannot change the TCP header today and expect the new protocol to actually work on the internet. There are too many in-network devices that will balk at this change, and many will outright reject or drop these packets. Anything that is exposed to the network becomes ossified. We learned this the hard way. The only way to ensure evolvability is to ensure that the protocol is end-to-end encrypted so that the network cannot know the protocol on the wire and cannot ossify it. Again, we learned this the hard way. In previous talks, I've talked about how the way early internal versions of Google QUIC, or GQuick as we call it now, had an unencrypted flag byte in the header. And this was immediately used by a middle box of a firewall vendor to as a quick identifier, basically as a protocol identifier. We learned that even a single unencrypted bit that we leave visible to the network is basically lost forever, that we can never change that bit again. This is not an exaggeration. Those of us burned by it know this to be a hard, bitter truth. So, this is basically our goal to encrypt everything was primarily to ensure that QUIC was evolvable. Today, everything that is encrypted within the QUIC header, which is like almost all of it, remains evolvable. That is, the QUIC transport, if deployed, is evolvable, and the community, has deployed it. We will come back to this, and we'll talk about this a bit more. So, with that, let me move on to the second part of the talk, which is QUIC's immediate value proposition. So, this is basically what QUIC was, but we are now going to talk about what the value of QUIC was, or how we sold it in other ways. QUIC broke new ground in several ways. The immediate benefit for the web was always reduced latency. Zero RTT transport and crypto handshake was a really important part of this. This basically meant that QUIC could get a quick using client, HTTP3 client could basically send user data along with the transport and crypto handshakes and not have to wait for the handshake to finish before sending data over. And this was hugely important. People often say that QUIC zero RTT is similar to TCP fast open with TLS 1.30 RTT, but it's not. Broadly speaking, TCP uses IP addresses as the endpoint identities, and TLS uses domain names. Now, this is a huge gap. All zero RTT methods use some sort of a cookie at the client that is reused on new connections to prove that this is a returning client. In a world where every server name maps to multiple IP addresses, TCP fast open simply does not do anything, since the kernel only reuses the cookie when a new connection is made to the same IP endpoint again. Note that TLS might still be able to do zero RTT, since that cookie is tied to the domain name. We fixed this gap in QUIC by having an endpoint identity that was basically the same for TLS as for the purposes of the handshake. Meaning that if TLS could do zero RTT, so would QUIC. This means that QUIC zero RTT is substantially more effective than when using TCP fast open with TLS, even in theory. Additionally, TCP fast open can send only one MTU worth of data in the first round trip time from the client to the server, since only one packet can be sent as the SYN. This limitation does not exist in QUIC. In practice, TCP fast open does not work so well on the internet to begin with. So there's still a substantial issue for clients with this because the separation between kernel and user context is a huge problem. I won't go into this here, but Chrome decided not to support TCP fast open because of privacy issues. The kernel is simply a different world with too weak an interface to user contexts. Of course, this API can be changed, but that's another long haul. With QUIC zero RTT, you also get to do one-shot messages with encryption and no additional delay. For instance, DNS transactions can now be encrypted in the common case with no additional latency for exchanging keys. For those of you familiar with it, this is TTCP or TCP for transactions, but really happening now and happening now in practice and better. All's not straightforward with zero RTT, however, and you'll hear more from Ian later about this today. So the second way in which QUIC broke new ground was through connection migration. This is something that we wanted for decades, and it's finally here with QUIC. But this is again fundamentally difficult to do with TCP and the split TLS TCP model. Those of you familiar with MPTCP will say, well, it's been there in TCP for some time now. But let me take this moment again to note that the inability of the ecosystem to evolve around TCP is a huge issue. It remains an issue. MPTCP still requires middle boxes and firewalls to play nice. Additionally, and importantly, there are still security issues that come from the separation of IP identity from the cryptographically secure identity of the endpoint that is used in the application above. By having TLS and QUIC wound together tightly, we don't share these issues. You are starting to see this recognition that tying these two together is important. It's showing up in proposals like TCP-LS that integrates TCP and TLS more tightly. But that has its issues in practice. Only time and effort will tell how far these efforts go in practice. The third way in which QUIC broke new ground is by enabling deep debugging and logging capabilities that are much easier to deploy. All the large server systems that I've encountered or worked with have rich logging capabilities deeply integrated with applications. Running applications have streaming logs with rich formatting and querying capabilities. Now compare this to like historical transport debugging capabilities where you need to get packet captures and PCAPs, log them separately. This usually requires an entirely new logging workflow and is typically entirely separate from the application logging workflows. Since QUIC is really built into user space and close to the application, or at least in application space, typically, QUIC applications typically leverage and use the same logging workflows that are available to the rest of the application. And this allows for cross-layer debugging with substantial ease. Again, those of us who've been burned by hours of staring at web or video logs and trying to correlate those with TCP connection traces to understand, to figure out problems, understand the value of joint deep logs. I believe you'll hear some of this today from Lucas later. To showcase this value, the value of deep logging and the value of the user space logging with QUIC, I want to share a demo of a debugging or a tracing idea that Kazuho Oku, my friend and Fastly colleague, and I came up with. Basically, consider this problem. You are a client and you're watching a video. Suddenly, you start to see poor performance. The best you can do is gather traces on the client side, on your side, and hope that you can get some clues out of it. And even if you were to share that, that's the best you can do. However, the most interesting trace typically is on the sender side. And this is on the server, however. So you might be able to get to the server side, assuming that you have some kind of access to get there. And now you need to still figure out exactly which of the many servers that you have that is this client connected to in order to basically have any hope of grabbing a trace. Or alternatively, you need to have some sort of client identifier that allows you to go fetch the trace from your log storage. Wouldn't it be great if the client could grab the server-side trace for just its connection directly without actually having to go and have access to the server? And if it could do that, a user with a problem could grab client-side trace, a server-side trace, and have a complete view of the transport connection. We built exactly that. Let me show you. And what I'm going to show you is a very simple demo of this. Okay, so here's a video to the left, and you're going to see this start to play. On the right, I'm launching a self-trace page, which effectively shows me a packet trace for the video that I'm watching. Now note, this is not a packet trace from the client's view. This is a packet trace that shows the server's view of this connection. This is literally a request that's going over the same connection as the video over to the server, and the server dumps its packet traces into the connection, compresses and dumps it into the connection so the client can display it. So right here, I've got the server's view of the connection. This is the equivalent of a PCAP from the server, but I'm able to get it right on my web interface here. An immediate promise of QUIC is in being able to leverage it for redoing server architecture. And I'm saying immediate promise because you're going to hear something today about this. I'm not going to go into the details of direct server return here. I believe Matt is going to be talking about that later today. But at a high level, QUIC introduces significant flexibility in how one can think about serving by divorcing a sender's view from the receiver's view. Without getting into the weeds here, separating these two views essentially means that we can optimize our serving architecture without requiring any changes to receivers or to clients. That is, we can shape the use of QUIC to efficiently fit our serving architecture without requiring any changes at the end users, potentially resulting in even lower latency to users and at lower cost to the servers. So those are the ways in which we convinced the world, so to speak, to deploy QUIC. And these are important ways. These are the huge benefits that you get simply for deploying QUIC. But there are other things that QUIC enables, and there are many things that QUIC is enabling today, and I want to talk about them now. First, we always wanted QUIC to basically be an enabler for new technologies, and at Fastly, we are using it to develop a new congestion controller called Pico. We are building reordering tolerance. Now, these things are doable in kernel for TCP as well, and I wouldn't argue that. They're a lot easier to try and to deploy within QUIC. You'll hear about some more experiments like this today, in discussion at least. Mask is a new suite of protocols that employs HTTP3 and QUIC to effectively create hidden tunnels. That's one way to think about it anyway. And this is a new-ish suite of protocols. However, I want to tell you that Apple's private relay, if you look up the documentation, uses mask technology to basically build its split VPN, I want to say, product. This is huge. Mask is a new technology which is still not fully standardized, built on top of QUIC, and we are using that already, and this is deployed very widely today, taking tons of traffic on the internet. And there's a new effort, finally, for doing media over QUIC. This is a new effort at the IETF called MOQ, MOC. And I think of this more as sort of the new world for WebRTC refugees, people who've been burned by working on WebRTC, the complexity of it, and looking over to QUIC to see if they can do it with a better, simpler transport that is built for that purpose. The reason they can do this, the reason we can do this, the reason we can think about this is because QUIC is evolving and can evolve to meet the needs of new applications. So what is the real value of QUIC? QUIC does make the web faster, more resilient, more responsive, but that's just the beginning. QUIC enables new technologies above it. It's a platform for building new things on top of it. And more importantly, it is a transport technology that can actually be evolved on the internet today. It is continuously evolving, and there are multiple versions already in parallel running today on the internet. So I submit to you that we've successfully pulled a sleight of hand. We used HTTP and the web as the vehicle to deploy QUIC into almost all server and client environments. And we've done this today. And in doing this, we created a path through an ossified internet for new end-to-end transports and technologies to thrive. With that, I'll end my talk. I thank you for your time, and I look forward to more discussion today.